Hello, so we're going to continue our journey through the wonderful world of wacky derivatives. Now, the story so far, as you can see on the screen here, is that we've got the following derivative rules. So we've got if f of x is equal to a constant number, so this is a number instead of no variables in it, then the derivative of the function is 0. If the function is x to the power of n, so x raised to a power, then the derivative is n times x to the power of n minus 1. So we take 1 away from the power, and then the original power is multiplied at the start. If f of x equals some number multiplied by x to the power of n, so we call that a, so ax to the power of n, then the derivative of the function is a times n, the original number that x was raised to, x to the power of n minus 1. Now do note with all these examples, well this example here and this example here, that x is raised to the power, not the whole thing. We would have to put brackets in if it was the whole thing. Okay, now the last thing we looked at was if we broke f of x down into two functions, and this would be true if we looked at 3 or 4 or 5 or 6 or 7 or 8 functions, but if it works for 2, it works for more. If we break f of x down into two functions, then the derivative is equal to the derivative of the first function plus the derivative of the second function. Now this works for anything, including stuff we haven't seen before. So if I said that f of x equals sine of x plus cos of x, for example, then f dash of x would be equal to whatever the derivative of sine of x is, plus whatever the derivative of cos of x is. Now we don't know what the derivatives are. We can work it out using limit theory, but we don't know what they are. But I'm just saying that it's that's how that rule works. In general, though, in this year, in methods foundations, in the unit we're doing, in the course we're doing this year, we're really limiting this idea to polynomials. So, in other words, if I've got f of x equal to, e.g., 3x squared plus 2x, I don't know, plus 1, then the derivative of the function is taking the derivative of each part in turn. So 3x squared becomes 6x, okay? So 2 minus 1 is 1, so x to the power of 1 is just x. 3 times 2 is 6. Plus 2, x to the power of 1 becomes x to the power of 0, and x to the power of 0 is just 1, so it's gone, and 1 times 2 is 2. And I don't have to write it in, but plus 0. This constant part of the polynomial, its derivative becomes equal to 0. Okay, so the derivative is 6x plus 2. Just a reminder, I want to keep on reminding you that the derivative function, this is a new function if you like, it's called the derivative function. It's the derivative function of the original function, and it describes the gradient. So by substituting a point in for x, we can describe what the gradient is at any point on the graph. That's the idea of it. That's why we kind of do it. And in a future lesson, what we'll do is we'll look at some applications of using the gradient function in order to solve problems from graphs or application problems. Okay, that's not the point of this video. The point of this video is to just continue to sort of broaden your understanding of derivatives in general. So what I want to have a look at is this. What about f of x equals g of x times h of x? Or what about f of x equals g of x divided by h of x? In those two cases, it would be fair enough to go that f dash of x is equal to g dash of x times h dash of x, and that in the second case there, we've got g of x over h of x, that would be g dash of x over h dash of x. That would be fair, wouldn't it? Because it kind of follows through from that rule as well. And remember that I use limit theories to show that if f of x equals g of x plus h of x, then f dash of x equals g dash of x plus h dash of x. So I showed that through limit theory. So it would be a reasonable thing just to assume that that's the case, right? Well, if you think that that would be the case, then I'm afraid that you would be either Mr. or Ms. Wrongity of Wrongtown, because unfortunately it is not the case. That does not work out. Now, in order to show you that it doesn't work out in a formal sense, I could go through limit theory. That's the bad news. It's about 10 minutes of videos and 5 pages of limit theory to demonstrate what g of x, h of x would look like. The good news is it's beyond this course. You don't have to. Instead, let me just illustrate why it doesn't work by looking at an example. Hooray for examples. Let's take f of x equals x plus 1 times 2x plus 1. Okay, so we're multiplying. Now, in this case, g of x is like x plus 1, and h of x is like 2x plus 1. In other words, we've got two expressions or two mini functions that have been multiplied together here and here. Okay, so that's what we've got. But let's have a look at what happens if I derive them separately. F dash of x, this is wrongity, wrong, remember? F dash of x equals the derivative of this. Now, how about I underline it and just use different colours? The derivative of x plus 1 would be 1, and we're multiplying it by the derivative of, let me use purple, of 2x plus 1, which would be 2. Okay? So x is raised to the power of 1, so it becomes 1 times x to the power of 0, so that's just 1. And the derivative of plus 1 is 0, so it would be 1 plus 0, which is 1. X to the power of 1, 2 times 1 is 2. X to the power of 0, so that would be 2. And this bit would go, derivative of 1 is 0, so it would just become 1 times 2. Okay, which we can write down as, change colours. Which we'll write down as 1 times 2, which is equal to 2. Okay, that kind of sounds neat and tidy and reasonable, but unfortunately it's not, and I'll show you why. So why is this one wrong? I'm going to put a big red line through it too, just to remind you, it is wrong. If I start from the start again, it's a good place to start, isn't it, at the start? X plus 1 times 2x plus 1. And then this time around, I will expand first and then derive it. Let's see what happens. So I've got x times 2x is 2x squared. Then I've got x times 1 is x. Then I've got 1 times 2x is 2x. And then I've got 1 times 1, which is 1. Okay, coolio. So collecting the like terms in the middle there, I've got 2x squared plus 3x plus 1. Now let's derive this. F dash of x must be equal to the derivative of each part of that polynomial. So the derivative of 2x squared is 4x. Okay? 2 times 2 is 4, 2 minus 1 is 1, so it's 4x. 3x becomes 3. 1 times 3 is 3, and x to the power of 0 is just 1, so it's just 3. And the constant term plus 1 disappears, so we're left with 4x plus 3. Now look at this. In the top one, which I've crossed out, we've got f dash of x is equal to 2. In the bottom one, I've got f dash of x equals 4x plus 3. They are not the same things. Now, one of the, I guess, beautiful things about mathematics is that you should be able to get consistent results, regardless of technique. And if you don't get consistent results, then there's a problem with the technique. In other words, the derivative of this function here, f of x, needs to be the same regardless of what technique you use to get it out. This technique got us equal to 2. This technique got us equal to 4x plus 3. Now with this technique, I used expansion, which is a proven thing, that we know that's right. I then used the derivatives of the individual parts of the polynomial. We know that works. We've done it in the past, and I've shown you some limit theory to demonstrate that that works. This is a proven way, unless I've made a mistake somewhere along the line, which I haven't, in my just basic calculations. Each step here is a proven step. In other words, we've done it in the past before. We know it's correct. This method here is not proven. And this is one of the dangers of mathematics that you need to be a bit careful of. And it's why I spent a video explaining to you why f of x equals g of x plus h of x, then f dash of x equals g dash of x plus h dash of x. Because I know that I could have just gone, well, it's obvious, isn't it? and that would sound reasonable. But then when you look at this one here, where I've got f of x equals g of x times h of x, that same sort of obvious step is not right. It's not true. It's demonstrably not working here. Okay, and I could give you another example, like f of x equals g of x over h of x. I could use something like f of x equals 2x on x, and you would see that that fails as well. Okay, so in mathematics, you need to be careful not to assume things as being correct, and it is important that you do take time out to, I guess, ensure that either through literature, i.e. reading from a textbook or something like that, or through using tried and true principles like limit theory, for example, that things that you think might be true, you need to make sure that they are true. And if you looked in a textbook, for example, not ours, because ours doesn't go this far, but you would see that the derivative of g of x times h of x is not that, and you would find that the derivative of g of x over h of x is not that. It's a bit of a nasty limit theory thing, like I said, so I'm not going to go through it, and you don't need to know it. So that's the important thing to know. How does this relate to our body of work this year? Well, what it means is that essentially, if this was the real world, then if you came up with a complicated function, like one with a fraction and whatever else, then you would need to explore more sophisticated ways of solving that problem if you needed to derive it, if you needed to work out a gradient function. That's in the real world, I guess, and that would come at a later stage of your development through calculus. In practice for this classroom, if we give you some problems this year that aren't in polynomial form, then odds are that you can do something about it to make it into polynomial form. If it looks like it's going to be two things multiplied together, maybe you can expand it. If it looks like it's a fraction, maybe you can cancel down the fraction. Importantly, there is something you can do in order to get it into polynomial form, because if you can't, then we're going to find it difficult to solve at this level or at this stage of your mathematics and your calculus. So that's the name of the game. But importantly too, in the real world again, if I dare say the real world again, it's also important for you to note that the techniques I'm about to show you, the problems that I show you, should also be applied in the real world. In that if you come up with some sort of function, you're given some sort of function, and you need to find the derivative, you need to find a gradient function so you can do stuff with it. The first thing you should always do is try and simplify the function, because the simpler you can make the function, the easier it is it's going to derive, and quite often the less likely it is you're going to come up with some silly mistakes. So keep that in mind, that even though we kind of know what's going on, it's probably worth working out exactly what you can do to simplify first of all. Now, I've just shown you an example here of what you should do if you come up with a factorized expression, like two things multiplied together, and you can imagine it could be three or four things multiplied together. Answer, expand it. Once it's expanded and simplified, it will be in polynomial form and easily derived. Let's have a look at a few other examples. These are just to I can't go through every single example in the world, but these examples hopefully will be enough to sort of give you an idea about what to do. So, example 1. F of x equals 4x to the power of 4 plus 2x over 2x squared. Let's make it 2x cubed. Okay, so there's my function there. I want to do what I can do. I want to do whatever I can do to get rid of that that fraction there. So what are we going to do? What I might do is give you a minute to try yourself, see what the steps might be in order to get rid of that fraction, and then you can come back to the video and see the solution. Okay, so the derivative is something that we will work towards. We're not there yet, we've got that polynomial going. So the first thing I will do is I will factorize the top. So here I've got 4x to the power of 4, here I've got 2x cubed. There's a common factor of 2. There's also a common factor of x cubed. But you know what? I'm going to take a step forward actually. And I'm going to say, look, I'm after getting rid of this x squared here. This is the important thing to get rid of, the x squared. So I'm not going to take out the highest common factor, unbelievably. I'm only going to take out what I need to get that bottom number, the bottom fraction. So I've got 2x squared there. So I'm going to take out just x squared. What does that leave me with? Well, that leaves me with 2x squared here. You know, you can just do the check to make sure. 2 2s are 4. X squared times x squared is x to the power of 4. And I've going to have x left here. 2 times 1 is 2. X squared times x is x cubed. Over 2x squared. Now that this is in factor form, this and this can cancel out. As long as I've got the whole of an expression multiplied the whole of another expression, cancelling out can happen. Remember, if there was a plus in there or something, we couldn't just cancel down like that. Like I couldn't cancel down those bits there because there's a sum in the middle. You can only cancel down when there's a product and multiplication. Okay, coolio, but there is though. 2x squared and 2x squared cancels out. And that leaves me with change the colour. That leaves me with 2x squared plus x. Okay, that's all right. Now that we've got a polynomial, we can just derive it. I know that's more, that you can factorise that more, but remember, we don't actually want to factorise it more. Because if we did, then we wouldn't be... remember, that rule doesn't work. Okay, this rule doesn't work, so we don't want it to be in product form. We want it to be in polynomial form. And now we can derive it. So therefore, f dash of x is equal to 4x plus 1. 2 times 2 is 4. Reduce the power by 1. 1 times 1 is 1. Reduce the power to x to the power of 0, which is just 1. So the derivative function, it's not very clear there, is it? F dash of x is equal to 4x plus 1. Okay? Easier to do than for me to explain, so I hope you can get that. By the way, let me just explain something else. I might just take a slightly easier problem, but I really should just say that, let's just say we've got f of x equals, I don't know, 3x squared plus 5 on 5, say, just to make it a little bit easier on me. Now, this is not in polynomial form yet, right? Because we've got a division all the way over by 5. All the way over by 5. So because of that, we need to be a little bit careful what we do. I think the best thing to do is probably split up the fraction first. So just keep in mind that if the whole fraction is over 5, that means, so sort of going in reverse, I can put each individual component over 5 as well. Yeah, it's probably safer to do that. So that would be 3x squared over 5 plus 5 over 5. And 3x squared over 5 is really 3/5 of x squared, and 5 over 5 is just 1. Okay, so therefore the derivative would be, I might just do this in a couple of steps so you can sort of see it. 3/5 times 2x to the power of 1, and the plus 1 would be gone. Okay, it's a constant term. And then I've got 3/5 times 2x. 3/5 times 2 is 6 over 5. So it's 6/5 x, or if you want, 6x on 5. Now, you would have got the same thing if you derived the top and then just left the 5 on the bottom. But I just wanted to say that you can break it up like this and get the right answer as well. I'd just be a little bit concerned if you didn't do that you might think that you have to derive the bottom and get 0 or something horrible like that, which you don't. You can see how splitting it up really helps. And that idea of splitting up a fraction will be useful a little bit later on as well, maybe not in this video though. Okay, let's have a look at a couple of other tricky examples. How about this one? Oops. Example 3. How about x? Oops, should actually start by saying the function. Let's just mix it up a bit too. Let's say y equals x squared minus 1 over x plus 1. Okay, so again, we've got a complex kind of denominator there, but if we can't get rid of that denominator in some way, or at least have no variables on the bottom, then we're a bit stuck until we know some more advanced rules. So kind of expect that there must be at this level. Otherwise, you probably say cannot be derived further as it stands. It can be, but you can't with the rules that you know. Okay, but x squared minus 1 is a difference of two squares. Okay, it's x squared minus 1 squared. So that's x minus 1 times x plus 1. Again, if you're a bit shaky on these kinds of rules, if you couldn't see straight away that the derivative of x squared minus 1, I don't know why I'm pointing at the screen for when it's down here. If you can't see that derivative of x squared minus 1 is, sorry, not derivative, that the factorised form of x squared minus 1 is x minus 1 times x plus 1, then that's going to be an issue because, again, we're trying to do hard things here. And if we're trying to do hard things and you're not too sure about the simple stuff, then you need to get practice into your system, okay, so that you can do these things without thinking too much. Okay, it's not a massive problem if you don't know how to do it. It just means you need to put more effort into to fix it. And if you don't do that, then you're going to find it really difficult. Okay, so I have factorized it. And now, because I've got these two things multiplied together, x minus 1 and x plus 1, so they're two factors multiplied together, and the whole of the bottom is an x plus 1, because I've got the right settings for that, means I can cancel out that whole of x plus 1 with that whole of x plus 1 there. Okay, which leaves us with the very nice, very simple expression x minus 1, which we can derive. So therefore, and I'm going to use my other notation now instead of f dash of x. I started with y, so I'm going to use dy by dx, small change in y over small change of x, is equal to, oh, that's pretty easy, 1. There we go. So that horrible expression at the start has a derivative quite simply of 1. Again, in case you weren't too sure, x is raised to the power of 1, and therefore it becomes 1 times 1 equals 1, and x to the power of 0 is 1, so it's just 1. Okay, let's have a look at another example. Example 4. Looks horrible, but it's not too bad. X squared plus 2x plus 1 all over x plus 1. And let's use y equals again, just to change it up a bit. Alrighty, here we go. So we need to see that the top of this is factorizable. It's a trinomial. Now, you can use whatever method you want to try and factorize it. Try not to use the factor theorem or something like that for something as simple as this as well. But fingers crossed that you can see that this is simply a perfect square. That's a square, that's a square, and when I multiply x times 1 and double it, I get 2x, I get the middle term. So this is just a perfect square. You should be able to do this without too much sweat. X plus 1, all squared, all over x plus 1. So we've got this squared over this expression here, and so I can basically cancel down one of the x plus 1s here with one of the x plus 1s on the top, which effectively just gets rid of that square. I hope that makes sense. Maybe I should just drag that out a little bit, just so it sort of makes sense to you. So x plus 1 all squared is x plus 1 times x plus 1, and therefore x plus 1 all squared over x plus 1 is equal to x plus 1 over x plus 1 over x plus 1. And I'm cancelling that out to give me my x plus 1. Okay, that's what I'm doing in my head there. I hope that makes sense. Alright, so what am I left with? I'm left with x plus 1. And therefore the derivative of that, dy by dx, is equal to 1. Again, so it looks horrible, but the derivative is simply equal to 1. Okay, last example, and I think that's about all I've got for the examples now. So again, just to reiterate those steps. So if you've got a horrible looking function, okay, if you've got a horrible looking function, what do? You look for ways of simplifying. You know what? That's basically it. So, e.g., is it a fraction? Can you cancel down? And cancelling down might, sorry, my pen's just run out, I think. And cancelling down, using my finger there, so it's going to get a bit tricky. So cancelling down might mean factorising the top or the bottom or both, and then dividing out stuff in order to make it work. Is it a factorised form? If it is, then maybe you can expand. But what you want to do is you want to get it into polynomial form. That's the name of the game. If you can get it into polynomial form, so I've got the spelling there, if you can get it into polynomial form, then you know that you've got a method for deriving the function. And that's what you need to do. Okay, good luck with that.